So today we will discuss about microprocessor and microcontrollers. Now, what is a microprocessor? So what is a microprocessor, right? Now, microprocessor is an integrated circuit which can perform all the functions as that of a CPU. It can perform all functions as that of a CPU, right? Like all arithmetic logic operations as that of ALU and can communicate with all connected devices. It's a VLSI chip. VLSI stands for Very Large Scale Integration Chip, VLSI chip. It has digital circuits and it can do arithmetic logic, communication, and control functions. When microprocessor is packaged as a printed circuit board plus interface memory chips, then it becomes a microcomputer. So we call it as a single board computer also. So microprocessor plus interface and memory chips. Then this becomes a microcomputer. Right? Or a single board computer also we can call it. So let us look at a architecture of a typical microcomputer. So a microcomputer has a control unit, then it has a instruction register, right? Then instruction decoder is there. Then ALU, arithmetic logic unit. Then there are some data registers. Okay, and this control unit interacts with instruction register, and this is the flow of the control. So this becomes a microcomputer, and then there is a bus which carries data, address, and control. So there are three types of bus. I will make a bus. They are the communication lines. So one is the data bus, another is address bus, and another is the control. Okay. And they are then these buses are connected to the control unit like this. Information can go towards the control unit and can also come out of the control unit. And then they are also connected to memory. There can be random access memory, read-only memory, EPROM, right? Then it is also, these buses are also connected to input-output devices. There can be analog to digital card, there can be digital to analog, or can be even digital to digital also, right? Then this bus is also connected to monitor or modem or the network, right? So this is the structure of a microcomputer, where we understand that a ROM is used for permanent storage of data that CPU can read, but CPU cannot write data to ROM, and ROM does not need power supply to retain data, whereas RAM, random access memory, that their data is lost when power is removed, right? So in the RAM, there are two types of RAM. One is static RAM and another is dynamic RAM. In static RAM, data is in flip-flops, whereas in dynamic RAM, the data is stored in, there are capacitors and the storage is in terms of capacitors. Now, microprocessors can be programmed using assembly language, which has a mnemonic command, right? And this assembly language is converted into a machine code by assembler. When we have a microprocessor, plus memory plus input output capabilities, so all of these things, when we get on one chip as a package, right, then it is called a microcontroller. So this becomes the microcontroller. So what we have in a microcontroller, there is a CPU, okay, then there is a RAM, okay, then there is ROM, then we have EPROM here, then we can also have, there can be EEPROM, right? Then there can be timers, analog to digital capability, then digital to analog capability, input output ports, right? So all of these things, when available on one product at one place, then it is called mm, a microcontroller. Now this becomes a microcontroller, right? And this EPROM, when this requires UV light for erasing, whereas this electrical erasable programmable read-only memory, this can be erased using electrical means. Now we will also uh, understand about PIC microcontroller. So PIC stands for peripheral interface controller. Okay, and in our syllabus we have PIC 16F84 microcontroller. It is 8-bit microcontroller with electrically erasable programmable read-only memory. And it has 13 input-output lines. Okay. This EEPROM has the size is 1792 bytes, and the size of RAM in this case is 68 bytes of RAM, right? And also it has 64 bytes of data memory. Now, whenever a microcontroller works, it has a clock, and that clock helps in timing of a microcontroller, and it works according to that clock. The clock speed in this PIC 16F84 microcontroller goes from speed can be from 4 to 10 megahertz, right? Now let me draw the schematic of PIC microcontroller. So here I am drawing the microcontroller now. So on other side we have 10, 11. Here it is RA1, RA0, SC1, SC oscillator 2, VDD, RB7, RB6, RB5, RB4, So the voltage of 5 volts is given through a resistance to pin number 4, right? And pin number 5 is grounded. Okay, and we have a oscillator or the clock, the crystal attached to OSC1 and 2 in this fashion. Here is the capacitor and it is grounded here. This capacitor can be 22 picofarad. And here we have the crystal here for clock. And this VDD is again connected to 5 volt here. And there is again capacitor 0.1 microfarad capacitor, and it is grounded here. Right, now this RA0 through RA4, RA0, this is RA0 here, this RA0, RA1, RA2, RA3, RA4 are digital input output pins. So RA0 through RA4 are digital input output pins, and we call them port A. It's also called port A. Right. Then RB0 through RB7 are also digital input output pins and input output pins, but they are called port B. Okay. Now this microcontroller also has the capacity to handle interrupts. Now, what is an interrupt? Interrupt is like I am recording a video or I'm audio message now, but if at this time the doorbell rings, then I will pause the this session and attend the doorbell. Now, this doorbell is the interrupt. Similarly, if microcontroller is performing some function, and if interrupt signal comes, then microcontroller will handle the interrupt first, and then after handling the interrupt, it will do the function it was already doing before the arrival of the interrupt. So pins RB0 through RB4, pins RB0 and RB4 through RB7 can be configured as interrupt pins. So pin RB0 and RB4, RB5, RB6 and RB7 can be configured as interrupt pins. Now we also have this MCLR pin. Now this is called master clear pin, and it is active when low, and it provides a reset feature, right? So when we have to reset the microcontroller, so this pin is used. Grounding this pin causes the PIC to reset and restart the program stored in the EEPROM, electrically erasable programmable read-only memory, right? And this pin must be held high during normal program execution. So one can design a reset switch to handle this pin 4, which is MCLR. So one way of handling it can be that here we have this pin number 4, which is MCLR, like this, and we are connecting it to 5 volt, of course, through a resistance, right? Typically it will be 1K resistance. So we can add a switch here. So it can be called a reset switch. When we want to reset, we can just press this switch and pin 4 would become active because it will become grounded, right? Now let us look at programming a PIC, how you can program a PIC. So software is written and compiled using a personal computer and then downloaded to the microcontroller ROM as machine code. Now the assembly language used to program a PIC 16F84 consists of 35 commands. And this set of commands is called a instruction set. So there are 35 commands. So some of the commands we will just try to see, like B, C, F, comma, B. Now this is one command. This means bit clear F. So what this command does? This clears bit B in file register F to 0, right? So what it does, it clears bit B in file register F. F is a file register to 0. So if we let us say have B, C, F port B, comma 1, let us say. So what will it do? It will make bit 1 in port B go low, right? It will make bit 1 in port B go to 0. Now what is port B? As you can see here, RB0 through RB7 is port B. So RB0, RB1, RB2, RB3, RB4, RB5, RB6, RB7. So these 8 pins together are called port B. Now this command, so there are 8 bits, right, in port B. Now in this port B, this command bcf port B comma 1 will make bit 1 in port B as 0. So if let us say port B is uh, all are 1, let us say 1, 2, 3, 4, 5, 6, 7, 8, right? So this is RB0, 1, 2, this is RB0, RB1, RB2, RB3, RB4, RB5, RB6, RB7. So this command will make this status as like this. So this is bit 1. So this bit 1 has become 0. Okay. So similarly, now let us understand another command in the assembly language. So that is movlwk. movlwk. So this means move literal to W, right? So let us take it an example. movlw 0xa8, right? Now hexadecimal constants are identified with 0x prefix. So when we write 0x prefix, this is a prefix, right? When we write this prefix, that means this is hexadecimal. We are talking about something which is hexadecimal. Okay. So what will it do? So this will store the hex A8 in the W register. This will store the hex A8 in the W register. Okay. So this hex A8 will get stored in this register. Move literal to W. This means move this to W. This thing into W. So A8 would get stored in W register. So this is a move command. Right. Now, similarly, there is another command RLF F comma D. So this means rotate F left. Rotate F left. So what it does, it shifts the bits in file register F to the left 1 bit and stores the result in F if D is 1, or in the accumulator if D is 0. Accumulator or the W register, right? So like suppose let us take it an example, RLF port B comma 1, right? And suppose the port B, you understand it is 8-bit going from RB0 to RB7, right? So let us say port B is right. Now this command, what will it do? It will make the status of port B as new status of port B will become 00 this will become the new status, right? So these are some commands, and like this, there are 35 commands of the assembly language, and this set of 35 commands is called instruction set. And if you want to program in assembly language, so you have to use these commands. Now, PIC programs can be written in a form of BASIC, also called PIC Basic Pro. So let us now look at PIC Basic Pro. Now let us look at PIC Basic Pro. So PIC Basic Pro compiler can compile these programs producing their assembly language equivalents, and this assembly code can then be converted to hexadecimal machine code that can be downloaded directly to the PIC EEPROM, right? So of course, you will require a programming device that can be attached to a personal computer. So this PIC Basic Pro is a higher level language, and let us try to understand it through a small program. So in PIC Basic Pro, so this is PIC Basic Pro example, right? So I port A.2. So what will it do is that it will make RA2 pin high. Second bit of port A, it will make high, right? And then pause 1000. So it will pause for 1000 milliseconds. Then we can write like low port A.2. It will again make the RA2 pin low, and then again you can pause, let us say, for 500 milliseconds. Now, if you want that this should keep on happening again and again, so we can use one command here, go to help, right? And here we can write help like this. So from here, the command, the control will go here, and the entire program now closes like this. At the end, we can write end. Correct. So this is one example of a programming PIC Basic Pro. Now, in any programming language, we have to create variables. The syntax for creating a variable is, let us look at the syntax. So syntax is, so first of all is name of the variable, then we write here variable, and then we write the type. So this is the syntax. So like my bit, now this becomes the name of the variable, and where var means it's a variable, and type is bit, it's a bit. Then similarly we can another byte, we can take the type example, my underscore byte, this is the name of the variable, and here we can write byte. So its type is it's a 8-bit. Now I can assign the values to these variables like this. Very straightforward. My underscore bit equal to 0. So it makes this variable my underscore bit as low. And I can assign a decimal value of 187 like this to the byte variable of type byte, which is my underscore byte. Okay. So now if we do take some examples more, like if I write it like LED VAR port B dot 0. So what will it do? So this would designate the variable LED as the state which is prevalent of pin RB0, right? RB0 pin, please recall we have seen this pin in the PIC microcontroller. Now similarly, if I write LED VAR my underscore byte dot 0, right? So what will it do? It will make LED as bit 0 of byte variable my underscore byte. So whatever is the status of bit 0 of my underscore byte variable, that will be given to the variable LED, right? So let us and when we have to define a array, so the syntax for defining an array is like this. Name var type size. Okay, so this is the syntax, right? So like one array by name values can be now defined like this. Values is an array variable and the size is 5, right? And for defining a constant, we use the short form con. And how do we use it? Let us try to see. Constant con 23. So this means this constant constant, this is a constant, and the value stored to it is 23. Now let us look at one another example of a program. My underscore count variable byte. So my underscore count is a variable of type byte, and target con 5. So we have a target is a constant with value 5, right? Now I also define my underscore button variable port 0, LED count variable A dot 0, LED underscore target variable port A dot 1. Now I am assigning the value my underscore count as 0. Now I am making this LED underscore count as low, right? So, and also I am making low as LED underscore target, right? Now we will see how we can begin. Now, while my underscore button is equal to 0, W, and so it will keep on, the control will keep on moving this while loop until my underscore button becomes 1. Now my underscore button, you can see, is the value which is available at 0 bit of port B. So whenever 5 volts will be given to 0 bit of port B, then only the control will come out of this while loop. And and here I can write high LED underscore count. So this will make LED underscore count variable high, right? Again, I can use the while command here. While my underscore button equal to 1 and W. And now this control will keep on circulating in this while loop until my underscore button again becomes 0. Now when it will become 0? When you can see my underscore, the value at my underscore button, it gets value from port B, the 0th bit. So whenever 0th bit of port B becomes 0. Right? So now let us see how we can use the if statement. If I can write the if statement like here, if my underscore count is greater than or equal to target, right? Then let us say, let us make LED underscore target as high. And here and if, right? And here we can write go to begin. And finally at the bottom, and okay. So this is the way it will keep on, this program would keep on running till target, this my underscore count becomes 5, right? So, but we have not, we are not incrementing my underscore count anywhere. So what we need to do is we need to increment it somewhere. Okay, so here we can insert it. So here we can write a command I underscore count is equal to my underscore count plus 1. So this is the one line, this is another 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 line, and this is the next line. Okay, and this is the next line, next line, next line, next line, and this is the last line. So this is a typical program in PIC Basic Pro for the microcontroller which we are discussing today, and that is PIC microcontroller PIC 16F84.